Arsen, who will tell us about testing assumptions of learning algorithms.
Yeah, thank you very much. So I'll talk about a joint work with Ronit, Aravind, Adam, and Kostas. So let's start. So first we'll talk about this framework that combines distribution testing with this model called agnostic learning. So agnostic learning is a very well studied framework in learning theory, and I'll start by explaining that. But first, let's go back to the most standard so-called pack learning, or sometimes it's called realizable pack learning. So what's that framework? So you have some function class f, let's say half spaces or low degrees or low depth circuits, monotone functions. So you have some class of functions. And here the functions we're going to study are going to be binary valued. So the value of the function is going to be 0 or 1. And so you have a learning algorithm. It gets this IID dataset S from some distribution D that's labeled by some function G in your function class. So our running example is going to be linear classifiers, also known as half spaces. So in d-dimensional space, there's going to be some hyperplane, and the function is going to have value 1 on one side of this hyperplane and value 0 on the other side of the hyperplane. And what we want the learning algorithm to do is to output a classifier f. And what's the guarantee that we're seeking the algorithm to satisfy is that the classifier output has a small error. So this means that if I take a new example x from the same distribution D, I want the probability that my classifier misclassifies it, output something that disagrees with G on that point, to be at most epsilon. Okay, so this is the most basic, what's called realizable agnostic learning. Realizable because there is a function G in your function class f that perfectly describes the data you're dealing with. So in particular, the error is at most epsilon means if you output, let's say, a classifier that's a little bit off, then it's still okay, as long as the probability it falls into this region where the two classifiers disagree is small. So agnostic learning is a more general setting that's also very well studied in learning theory. And here, the function G you're trying to learn can actually be anything, right? So there's no restriction on the function you're trying to learn. But what's different is the guarantee you're trying to achieve. So instead of trying to achieve error at most epsilon, as in the standard setting, what you want is you want the classifier you're outputting to be competitive with the best classifier in your function class. So if the best half space achieves error, let's say 0.1, I want my error to be at most 0.1 plus epsilon. Okay, most generally, we'll have this quantity called opt. So opt is the best error achievable among all the classifiers in your function class. So our running example is going to be half spaces or linear classifiers. So you want the classifier you output to be competitive with the best classifier in your function class. Okay, and yeah, so the way we're going to talk about this is learning the function. This is what it means to learn the function class f agnostically. Okay, so any questions for anyone? Okay. So the framework of agnostic learning has a reputation of being difficult because there are a lot of computational hardness results in the agnostic learning setting. So for example, for the same function class of half spaces, if your distribution on the examples D can be anything, if there's no restriction on your distribution on the examples, then there is no algorithm known that does better than to the D time. So statistically, you can do poly D over epsilon, but in terms of runtime, so this talk will be focused on the runtime. There's nothing, there's no algorithm known that's non-trivial for the linear classifiers. And there are all kinds of actual hardness results for this problem. So how do you get around it? So it turns out you can get very fast non-trivial algorithms if you make distributional assumptions on the data you're getting. So instead of saying my distribution D can be anything, you say, okay, my distribution is, let's say, uniform on the Boolean cube, or it comes from the Gaussian distribution, and so on and so forth. Okay, and then it turns out you can have like non-trivial fast runtimes, and there's a huge number of papers studying this setting for half spaces or for other classes, how to agnostically learn these function classes under these various specific distributions. So to summarize, agnostic learning is this very well studied framework in learning theory that handles data sets that cannot be perfectly described by a function in your function class. And so informally, the way I like to think about it is you want to fit the best function in your function class, your data set. Yeah, so like someone gives me a data set, I want to get the best linear classifier for this data set. If there's no linear classifier that does perfectly, but I want to do the best I can, up to error epsilon. And if you don't assume anything about the distribution where your data set is drawn from, like there's a lot of hardness results, but if you make assumptions like it came from uniform distribution or it came from the Gaussian distribution, then you can do a lot. But here's the problem. Right, so like if you're lying in your bed trying to fall asleep, but like the thoughts, but you can't fall asleep because maybe your classifier is not the best it can be. You cannot say, oh, it's okay. The theorem 1.2 in this paper says it's absolutely optimal, because what if your data set didn't come from the uniform distribution? So if you think about it this way, then like the real guarantee one of these theorems is that either, let's say, your data set came from the uniform distribution, in which case the classifier you get like kind of does the best it can do, is epsilon competitive with the best, let's say, linear classifier. Or if the assumption didn't hold, then all bets are off. The premise of the theorem doesn't hold, so you cannot use the conclusion of the theorem. And what's even worse, by just looking on the data set, it's not clear which of these two cases you are. Right? So, and like another thing you can try is, okay, like you take your classifier f, you can estimate, what's the error of my classifier. But the issue is that you can't check, you don't know what's the optimum, right? So, maybe your classifier has an error, 0.3, but maybe there's a classifier somewhere that does much, much better. Yeah, so these theorems, the point of those theorems is that they guarantee that like you cannot squeeze more out of your linear classifier on this data set, right? But if you don't know anything about the distribution in advance, maybe you can get a classifier that's a lot better. It's just the algorithm you're using is not the best one. Okay, so let's go back to connecting this to Clement's talk. So as you know, there are a lot of very interesting work on distribution testing. And as Clement talked, as Clement explained to you, the runtimes or sample complexities you get are something like square root of your domain size. And here the domain size, for example, when you're dealing with uniform distribution on 0, 1 to the d, is to the d, right? So, okay, what about you use one of these uniformity testers, make sure that it's accepting, and then hopefully you can use one of these learning algorithms, and then you'll be confident in the agnostic learning guarantee. And unfortunately, in learning theory, you care about runtimes that are much faster than this. So ideally, you want a runtime that's polynomial in all the parameters. And what's called dimension efficient runtime is d to something that only depends on epsilon. So that's also good. And maybe even 2 to the square root d is a good runtime. So occasionally you can. That's also acceptable. But 2 to the d over 2 far exceeds all these runtimes that people really want to achieve in learning theory. So if you want to use this tester first before running one of these algorithms, the runtime, the sample complexity and the runtime of the tester will far exceed the runtimes of the algorithms that you want to use, that you're using this tester to decide, can I use this algorithm or not? So, okay. So just to summarize again, yeah, I encourage you to read Clement's great book. But like off-the-shelf, let's say uniformity testers, they're too slow, like, and too for this specific purpose. So, however, we'll see that the ideas from distribution testing will be very useful for us. But before going there, I want to present to you the framework. So the idea here is to sidestep this hardness result for uniformity testing or for other distribution testing. But instead of asking, is my distribution close in dv distance to, let's say, uniform distribution, I want to ask, is it good enough for me to be able to use one of these agnostic learning algorithms and be confident in the agnostic learning guarantee? So here's the framework. So now the learning algorithm, so we'll call it a testable agnostic learning algorithm. It has 2 options. It can accept and give a classifier f, or it can look at your data set and say, assumption doesn't hold. Yeah. So it can say reject. So instead of just doing the same thing and outputting a classifier, the hope is that if the assumption is really bad, if the assumption doesn't hold, instead of outputting something that's very suboptimal, it's going to say reject. Okay. And here's the 2 conditions that we wanted to satisfy. So the first is completeness. So if the assumption actually holds, so let's say the distribution is uniform or Gaussian or like whatever other assumption you're using, if the assumption holds, I want, with high probability, I want the classifier to accept, the learning algorithm to accept and output a good classifier that's almost optimal. So completeness means I want to generalize this notion of regular agnostic learning. Yeah, so that's what it means. And soundness means like if my algorithm is accepting, I want to be very confident that the thing I'm getting is approximately optimal, right? So if my algorithm accepts, then I want the error of the classifier I'm getting to be at most L plus epsilon. So this way, if I get some data set, I run the algorithm on it, and I get my classifier, then I can be confident if it didn't reject, then I can be confident that the thing I'm getting has a error at most L plus epsilon. Okay. So now I'll talk about this first big tool that we developed for developing this type of algorithm called moment matching. So in our work with Ronit, we showed that for the class of half spaces, this can actually be achieved. For example, so both when your assumption is uniformity on 0, 1 to the d, and for the Gaussian distribution, you can do this in time d to the poly 1 over epsilon. And this matches up to this power of epsilon the best learning algorithms, just agnostic learning of half spaces under these distributions, like where you don't need to test, right? And consequently, by this wonderful work of Gottari and Clivens, they actually improved it all the way to d to the 1 over epsilon squared. So this testable agnostic learning, it's kind of free. It costs as much as like regular agnostic learning. And this 1 over epsilon squared widely considered to be optimal due to, at this point, we have cryptographic lower bounds too. So what does it mean? So what's the moment matching test? It's a very straightforward testing algorithm. You do the following. So you get a bunch of samples. So K, so K is going to be, instead of domain size, it's going to be degree of a polynomial in this tag. So let me write it here. So you take a bunch of samples, something like d to the k samples, and then you iterate over all monomials of degree at most k, right? So you iterate over all monomials, and then you compute the average of this monomial on your data set that you got, and you compare it what this average should be in expectation, if the assumption was satisfied. So you compute these two averages. And if this averages are too far away, but they should be close if the assumption actually holds. If they're too far away, for one of the low degree monomials, you reject. Otherwise, you continue iterating over all monomials, and if this test passes for all of them, then you say accept. Yeah, anyone has any questions? Yeah, feel free to interrupt. And I would like to note that if for the uniform distribution, this is exactly the k-wise independent tester that Clement was talking about earlier. That's been studied earlier. So our work kind of generalizes it to other distributions like Gaussian, for example. Right? So you basically check that to low degree polynomials, your distribution looks similar to the like this distribution you're assuming. Yeah, so uniform or Gaussian. So in terms of, so that's how you decide, am I accepting or am I rejecting? So how do we do the learning? So there's this very general tool in learning theory that's called, it's a paradigm of agnostic learning from approximation, and uses this wonderful algorithm by Kalai, Clivans, Mansour, and Servedia. And so this is a very general tool that lets you prove things. So it tells you prove things. You just need to prove a fact from approximation theory, and then this algorithm, their framework automatically transforms it into an agnostic learning algorithm. So what does it say? So if you're a function class, so let's say half spaces, this works for other classes too. If every single function in your function class is well approximated by a low degree polynomial with respect to the distribution D in L1 norm, so as a formula, this is what you want to prove. So for half spaces, you want to prove that every half space well approximated by a low degree polynomial. So in the sense that if you take the difference, take the absolute value, and take the average with respect to your distribution D, there's a polynomial for which this distance is at most epsilon. Okay, and the theorem in their work says if this is true, then this algorithm we are running will satisfy the agnostic learning algorithm and the agnostic learning guarantee. And the runtime you get is d to the k. So k is a degree of this polynomial. So lower degree, faster the algorithm. Right? So what does it mean? So combining this low degree tester with this notion, with this paradigm of agnostic learning from low degree approximation. So algorithms, so this is what we use for the algorithm. So kind of the tough part is how do you analyze this? And so what's known? So for a while it was known that, let's say, with respect to the uniform distribution on 0, 1 to the d, half spaces are well approximated by low degree polynomials, right? So this is what you use for the regular, not testable agnostic learning of half spaces. But to analyze this testable agnostic learning algorithm, you need a stronger, approximation statement that not only half spaces are well approximated by low degree polynomials with respect to the uniform distribution on 0, 1 to the d. But they're also well approximated by low degree polynomials even with respect to k-wise independent distributions, right? So if you're for k equals 1 over epsilon to the 4th. Yeah, so you want to generalize this statement. You want to prove it. You want to say this is true not just for uniform, but also for k-wise independent distributions. And our original proof used these tools from Chebyshev approximation and so on. But I'll talk about a different proof that was proposed for Galakota, Clivans, and Kotari. So it's not it's not going to be self-contained, but it's going to reduce it to well-studied question in pseudo-randomness. Yes, there's this surprising connection to pseudo-randomness that GKK 2023 has found. And so the central notion here is this notion of sandwiching polynomials. Okay, so you say a function f has a sandwiching degree at most k with accuracy parameter epsilon if there's a pair of polynomials, p up and p down. So on one hand, for every point x, the value f of x is sandwiched between p down of x and p up of x. So that's the first condition. And the second condition is these two polynomials are close to each other on average. If I average over the uniform distribution, the difference between p up and p down is going to be at most epsilon. Okay. So what they show is that if every function in my function class indeed can be sandwiched in this sense by a pair of polynomials, then this statement earlier, you can conclude this statement about every function in my function class F. Yeah, so every function in my function class F will be well approximated by a low degree polynomial with respect to a k-wise independent distribution. And the proof is 2 lines actually. So what's the polynomial I'm going to take? I'm going to take p down. So this is their proof from GKK 2023. So I'm going to take the polynomial to be p down. And okay, so f is sandwiched between p up and p down. So this average L1 error will be at most the average of p up minus p down, averaged over my k-wise independent distribution D. But wait, D is k-wise independent. So and the polynomials are also of degree at most k. So this average with respect to distribution D will be the same as the average with respect to uniform distribution of 0, 1 to the k. Yeah. So this is because every monomial only depends on k different variables. And now, And now I know that on the average the distance of the two polynomials is small. So we get this is at most epsilon. So this is how this lemma. Yes.
You don't need this for any distribution which is close to being k-wise independent?
Yeah, great question. So you do. So because you have this, so you that's correct. So if your tester passes, it's not exactly 0. Yeah. So you know that your distribution is close to k-wise independent, and the secret there is that so your runtime is d to the k, right? So you can assume, so it's going to be like epsilon divided by d to the k, close to the uniform distribution. And then you can take all these proofs I'm telling you, and you can check that this error will not be amplified. Yeah, that's a great question. Okay. Any other questions? Okay. But okay, how do we bound the sandwiching degree for half spaces, right? So now we want to prove that there's this pair of polynomials that sandwiches very tightly, let's say every half space. And this turns out to be very connected to this very well-studied notion in pseudo-randomness called fooling. Yeah, so in pseudo-randomness, people really care about like they have some function f, let's say a half space, and they want to approximate the average of this half space over the uniform distribution. But they want to have a deterministic algorithm that does it, right? And a very popular method for doing it in pseudo-randomness is so you can't query it on a bunch of random inputs because you don't have access to random bits. But what you can do is you can use a k-wise independent distribution. Yeah, so a k-wise independent distribution, there are the standard families that you can get by using your favorite k-wise independent hash family. So there are k-wise independent distributions that have support size of only d to the k. Right? So naively, you would have to query your function on every single input of 0, 1 to the d. So that's 2 to the d inputs. But there are k-wise independent distributions whose support size is only d to the k, so a lot smaller than 2 to the d. But then there's a question, OK, so I queried everything in the support size of this k-wise independent distribution. I computed the average. Now I know the expectation of this f of x, average with respect to some k-wise independent distribution. And now the question is this a good approximation or is it not, right? And there's this notion, and because of this, people in pseudo-randomness have studied a lot this question. But can I approximate the average of my function f with respect to uniform distribution with the average with respect to a k-wise independent distribution? And for a lot of function classes, such as half spaces, low-degree circuits, and so on and so forth, they've proven indeed you can do it for appropriate k. And why is this relevant? Is that there is this wonderful result from 2007 by El-Bazi that shows that this notion of fooling is exactly equivalent to this function of sandwiching that I mentioned earlier. And this looks quite mysterious, but this is a direct application of strong LP duality. So if you're teaching a course that covers strong LP duality, you can put this as a homework problem to show that these two things are equivalent. So this way, you can start with the results from pseudo-randomness and directly conclude that there is a pair of polynomials p up and p down that satisfy the sandwiching property. And so overall, this is the sequence of reasoning that you get, right? So you start with a fooling result from pseudo-randomness. You can use this duality, this result based on LP duality, to conclude there is a pair of sandwiching polynomials for every function in your function class. Then you can conclude that they are well approximated by low-degree polynomials with respect to the k-wise independent distributions. And then you can use KKMS to conclude that this algorithm is going to learn half spaces or other function class you are dealing with respect to k-wise independent distributions. And finally, combined with the moment matching test, you can conclude that the algorithm of KKMS together with the moment matching test is going to give you a testable learning algorithm for your class. And this type of reasoning also works for Gaussian distribution and for other classes. So this Golakota, Clivens, and Kotari gave this very general framework by kind of taking these results that people spent years proving in pseudo-randomness and getting testable agnostic learning algorithms from them. And surprisingly, there is also separation. So first time that we considered the moment matching test, I thought we could get everything. We can get testable agnostic learning algorithms for every class for which there are agnostic learning algorithms. But that turns out to be not true. So for example, monotone functions and convex sets with respect to uniform distribution on 0, 1 to the d and Gaussian distribution respectively, you can agnostically learn these classes in time something like 2 to the square root d. But it turns out that for testable agnostic learning, you provably need something like 2 to the d. samples. And kind of the reason at the core for it is that for half spaces, you are able to extend the approximation fact from approximation with respect to uniform distribution to approximation with respect to the k-wise independent distributions. And for these other classes, like uniform, like monotone functions on 0, 1 to the d, you cannot. Turns out you cannot do this step. So like this statement is like actually false. With respect to k-wise independent distributions, you cannot approximate monotone distributions well. And okay. So let's talk a bit about subsequent work. So so the algorithms I talked about earlier were all d to the some function of epsilon, like d to the 1 over epsilon squared. And in subsequent work, we developed, we studied algorithms that run faster. So if you're insisting on this op plus epsilon guarantee, then there you cannot really do better than d to the 1 over epsilon squared runtime. Because of their lower bounds. Now, we've had statistical query lower bounds for a while. Now we also have cryptographic lower bounds for this problem. And because of that, people study the so-called semi-agnostic setting, where instead of trying to achieve O plus epsilon, you are aiming for some constant times O plus epsilon. And this has been known since 2014 that this can be achieved in time poly d over epsilon. And in our work with Golokata, Clive, and Stavropoulos, we give an algorithm that does the same thing but is also testable. Okay, and this is I need to say this is with respect to the Gaussian distribution. Any questions? Yeah, so I won't be able to go into detail about how this works because just like this algorithm that does poly d over epsilon. It's it's quite involved, but to describe, I think like you need an hour or hour and a half to describe that. Yeah.
So is the difference between opt and d goal of opt, is it like, oh, you just need like factor 2, or is it more like, oh, it's going to be a giant constant? Is it
Great. So I'm not sure what the constant is because we inherited from that work, but there is work for decreasing it. So there has been subsequent work for like making the constant. You can make it as small as you want, but to make that testable, you would need to continue, you would need to develop new things. Yeah, so hopefully we could get also testable algorithms. Hopefully subsequent work will do it. Yeah. Yeah, there's no barrier, I know, for getting that. Thanks. Yeah, and sort of the obstacle even here is that if you run the moment test, then checking something like 1 over epsilon squared moments, so even that you cannot do in the runtime budget you have. So that takes something like d to the 1 over epsilon squared time. So you have to develop testers that go beyond this low degree moment matching approach. And now I'll just describe the tester we use, but I will not be able to talk too much about the analysis. So here's what it does. So first, we run these algorithms that give you, so you run one of these algorithms, you get a hypothesis, v hat. Yeah, so this is the half space. Yeah, so if it actually was Gaussian, v hat would be a good vector that has error of O plus epsilon. Okay. Any questions? Okay. So then what you do is you break your d-dimensional space into a bunch of the strips, okay, along that go perpendicular to this vector v hat. So you take your data set that you have and you compute the inner product with v hat, and you assign the point to an appropriate bucket depending on what this inner product is. And, if this was actually the Gaussian distribution, then very few points would fall outside of this minus square root log 1 over epsilon to square root log 1 over epsilon. If there are too many points there, it's not Gaussian, you reject. Okay. Otherwise, you go ahead, you assign each of these points to the appropriate bucket, So if it's again, you can compute that if the distribution was actually Gaussian, then all of these buckets would have something like between epsilon and epsilon squared and 10 epsilon points. So you check that holds. It doesn't hold, it's not Gaussian, you reject. So then, so this is sort of the main part. You loop over all the buckets. You project all the points you have within the bucket to this perpendicular subspace of V hat. So again, if the distribution was actually Gaussian, if you project down to a subspace, it should be a d-1 dimensional Gaussian, right? Because the projection here and projection here, they should be independent from each other. And what you do is you run the degree 4 moment matching test to the things you get for each of these buckets after projecting to the d-1 dimensional subspace. So this is the overall tester that we learned. And we show that you can go over these arguments that they had in those papers. And with more work, you can show that if your distribution satisfies this test, then everything works out and your error is O plus epsilon. And okay, so I'll have to go through this part a bit fast. Yeah. Yeah, so even just regular agnostic learning, nothing is known. Like forget about testing. Yeah, that's I haven't worked on it myself that much, but it seems to be an interesting question. Yeah. The best, I mean, it's known d to the poly 1 over epsilon is known, but nothing better is known. Okay. And so like another very nice thing about this work of Abashti, Balkan, and Long is that it doesn't work just for Gaussian distribution. It works for any isotropic log concave distribution. So those are things like if you have a convex set, like uniform of a convex set, so that's a log concave distribution, for example. More generally, those are distributions. If you take the log, the thing you get is a concave. Yeah. So Gaussian is one, but there's like a lot more others. And but the algorithm I just described, if the distribution is not Gaussian, it will reject, right? So and like a really nice thing about this algorithm, it's not just for every distribution in the class you have an algorithm. But there's like one algorithm that works for every single distribution in the class of isotropic log concave distributions. And so in this subsequent work, we introduce this notion of universal testable agnostic learning algorithms. So here again, instead of so you want your testable agnostic learning algorithm to not just accept, let's say, Gaussian distribution, or not just accept like one specific distribution, but you want to accept every single, like no matter which distribution in the class I'm dealing with, I want my algorithm to accept. Okay? And turns out we can achieve this. So for strongly log concave distributions, we can achieve this unconditionally. And for if you believe this very well-known conjecture in convex geometry called KLS conjecture, then our testable agnostic learning will accept every single isotropic log concave distribution. And there's this one here. There's surprising connections to sum of squares and convex semi-definite relaxations. And just this couple words about this is. So kind of the insight here is that, consider, like here's something that's true about the log concave distribution. If I project it to some unit vector v, then the kth power, expected kth power of this projection, will be at most something like k factorial, okay? And this is something that this algorithms, this learning algorithms, they use it. But like here's a problem. So computing this maximum or approximating this maximum for k equals 2, this is a computation of the largest eigenvalue of some matrix. You can do this fast. But for k equals 3, this is not known how to do. I believe there might be some hardness results too. Like computing, like I give you a data set, what's the maximum of this expectation with respect to all unit vectors? For k equals 3 even, we don't know how to do it, like non-trivial time. But so how can you do, how you can go around it, right? Because our algorithm should work, for any distribution, for any data set. And so, okay, let's go beyond worst case analysis. Let's study the average case version. So what about I say I need to, I want my algorithm to accept, to say yes if if it comes from the strongly low concave distribution. So, if you allow like a two-sided tester, then this problem is trivial because you can always say yes. And if it comes from the isotropic low concave distribution, then this maximum will be small. But in this very interesting work by Kothari and Steinhardt, they did the certification version, or like one-sided testing version of this problem. So here you're given an arbitrary data set. So if it comes from the isotropic low concave distribution, you should not only say yes, but you should output a certificate that this maximum is not too big. Okay. So I give you a bunch of data points from the strongly low concave distribution, not a worst case data set. A data set that comes from like one of this distribution, you don't know which. And you want to output a proof, a certificate, that this maximum v dot x to the k is not too big for all directions in the d-dimensional space. And they show that you can actually do this. And this is where this KLS conjecture comes in. So they show it how to do this unconditionally for strongly low concave distributions, and they can do it for all low concave distributions, assuming KLS. This conjecture from the theory of convex functions. Okay, so here's a couple open problems about testable agnostic learning. So one, if you want to do this O plus epsilon, so all the results we know, they follow from this sandwiching polynomial approach. So is this tight? Yeah, can you go beyond the moment of sandwiching polynomials, or do they characterize testable agnostic learning? And another open problem is like there are still gaps, for example, for intersections, for agnostic testable learning of intersections of half spaces. It's an end of a bunch of L half spaces. Yeah, what's the best runtime for testable agnostic learning of that class? And what other assumptions can you do assumption testing for? And now I'll talk about more recent work about testing a different assumption of learning algorithms, of whether there is distribution shift or not. So let's go back to, so here we'll focus on realizable setting. So what do you want? So one way to rephrase the standard PAC learning framework in learning theory is as follows. So there's some training data set you have. Like you have a bunch of images, or like a bunch of data points. They come with labels, +1 or -1. But then you have another unlabeled data set as test that you really want to classify, but you don't have the labels for it, right? And then what you want your learning algorithm is to assign labels to this data set. Yeah, so this is entirely equivalent to more or less equivalent to the standard PAC learning the framework that we talked about earlier. And so this is the framework. And a critical assumption this framework makes is that the distribution for which your training data set came is the same distribution as this other distribution from which the unlabeled data set as test comes from, that you actually want to label. But in practice, it turns out that a lot of times people train a classifier on some data set, and then they try to deploy it, and like something changes, something like that seems insignificant is different. Like for example, like the X-ray machine is different, or like there's something is not the same, and the classifier performs horribly, and like it can make incorrect decisions. It can, like without even warning the user, it can start making wrong, harmful decisions without us knowing about this. And this happens all the time in machine learning, and nowadays it's a big priority to try to make them more robust in this sense, and try to mitigate the distribution shift. So because of that, a lot of times you try to deploy it, and the classifier starts outputting nonsense answers instead of performing appropriately, and people have no idea when this happens, why this happens. So a big priority in machine learning nowadays is to try to mitigate this distribution shift problem. So again, what's the concern? Is that this data set on which you trained your classifier is not the same as the data set on which you are deploying it afterwards. And because of that, it might have a terribly high error on this other data set as test. And so here we introduce a framework where the design principle is that instead of outputting bad incorrect labels, I wanted to say, this is not the same distribution. I refuse to classify. And the framework is very different. Also, how many minutes I have? 10, 15? Okay. Yeah, I think that's enough for me. Okay, again, instead of just blindly going ahead and classifying this data set as test, your learning algorithm has two options. Either it says accept and gives you a bunch of labels, or it says reject, I think there is distribution shift. Okay, and we call this framework testable learning with distribution shift, or TDS learning. And again, there is two conditions that are very similar to the conditions in the testable agnostic learning framework. So there's completeness. That basically says this framework should generalize the standard pack learning. So if the distributions were the same, then with high probability, your algorithm should be in this case. It should say accept. And on the other hand, again, so if you want to say if your algorithm says accept, then I want to be confident in the labels that it's giving. Right, so no matter what this other distribution is, no matter how it's shifted, if my algorithm is saying accept, then the error of f should be small. Yeah, so the fraction of the data set on which it gives predictions that are not the same as this original labeling function g should be small. Okay, question? Yeah.
The labeling function is the same.
Yes, we have a version. There's a generalization where it can't even not be the same, but yeah. So it can be slightly different as long as on the both of these distributions the difference is, the error is small. The difference is small between two functions. But in this talk, it will be the same. Yeah. Okay. So in our work, we developed general methods for developing these algorithms in this TDS model. So, and yeah, just one thing I want to emphasize is that we'll be assuming that this training distribution is Gaussian or uniform on the cube, and so on. So the assumption we're testing is is there a shift or not? Okay. Just for all of us to be on the same page. And there are a couple existing works that handle related but not the same setting. So there's this notion of domain adaptation. And there are these very interesting papers about this. What they say is that if you were able to compute this quantity, it's not too important what it is. If you could compute this and check it small, then you'd be done. You could accept or reject based on that, and it would satisfy this definition we propose. And so this kind of solves the problem in the statistical sense. But in terms of runtime, it has this enumeration over all pairs of functions in your function class. It's not clear how to compute this thing efficiently. Okay. So, the algorithms for computing this thing, nothing is known better than 2 to the d. So this work, it mostly deals with the statistical aspects of the problem, while we work on the computational So, and also the framework is not exact. Their framework is more general. So instead of just guaranteeing the difference, the error is small, you can have you can kind of compute a bound. So then there's this other wonderful line of work on this framework called PQ learning. That's more general than the DDS learning framework we propose. And there again, so pretty much all the results are about statistical, about how many samples you need, as opposed to the runtime. So one exception is the class of parities. So for parities, it's known how to have computationally efficient PQ learning algorithms, but for all the other classes, there's still something like 2 to the D, all the known algorithms in this PQ learning model. Okay, and so one thing I want to get across before the talk is over is that again, this idea of moment matching is also very useful for the DDS learning framework as well. So again, what do? It's very similar to the testable learning algorithm. You take your data set, you go over all low degree monomials M, and you compute the average of your data set, and you compare with what this average should be if there was no distribution shift. Yeah, if the let's say distribution was uniform on 0, 1 to the D, it stays uniform on 0, 1 to the D. And the learning algorithm does something very similar to what KKMS does. It feeds the best low degree polynomial to your data, and it outputs the sign of that polynomial. Yeah, if all the tests pass. Yeah, if any of these tests fails, you say reject, and you refuse to label the data set. And this also works for other distributions, let's say Gaussian and so on. And sort of the insight again that analyzing this approach is also very related to the sandwiching polynomials I was talking about earlier. And to analyze it, we use this more stringent notion of L2 sandwiching polynomials. So again, you want to show that for every function in your function class, first there is a pair of polynomials that f is between p down and p up for every input point x. But instead of having the guarantee that the average absolute difference between the two polynomials is small, you want the average square of the two polynomials to be small. So this is like a more stringent notion. And we show that, again, if your function class satisfies this L2 sandwiching bound, then from that you can conclude that this moment matching algorithm that we described earlier is indeed satisfying the DDS learning guarantee. And to actually prove this L2 sandwiching bounds, what we do is we go into those papers from pseudorandomness that show this regular sandwiching degree bounds. And we show that you can strengthen those papers to also give a bound on this more stringent L2 sandwiching degree for function classes such as intersections of half spaces, for example. And yeah, so as I mentioned, so this is because the standard sandwiching degree is very related to this notion of fooling. So using the same techniques from those same papers that prove fooling, we're able to show this stronger. So they automatically imply the regular sandwiching degree bounds, but we show you can also get L2 sandwiching degree bounds. Okay. So finally, somewhat surprisingly, we show that you can even do better for example, for half spaces under the Gaussian distribution. You can do better than this moment matching approach for DDS learning. So we show that moment matching gives you something like d to the 1 over epsilon squared. It's the same type of thing it gives you for testable agnostic learning. But for DDS learning, we show you can actually get d to the log 1 over epsilon. So dependence on epsilon is a lot better here. And somewhat surprisingly, it turns out this log is in some sense inherent. So I guess naively you would hope, okay, you can get d to the log 1 over epsilon. Maybe you can get all the way, like poly d over epsilon. But we give a statistical query lower bound for that. So in particular, you cannot do d to the log to the 0.9, 1 over epsilon for TDS learning of half spaces under Gaussian distribution. And yeah, here's some couple open problems. So we were able to do this, to go from d to the 1 over epsilon squared to d to the log 1 over epsilon for the class of half spaces under Gaussian distribution. So can you also do this for the uniform distribution on 0, 1 to the d? So can you get TDS learning in that setting? So best we know is what you get from what you get from moment matching approach. That's d to the 1 over epsilon squared. Even more ambitiously, what about not assuming anything about your training distribution? Right. So if there's no noise, if there's a half space that perfectly fits the data set, then in the standard learning, pack learning, if you fit any half space that perfectly describes your data, then this is a pack learning algorithm that runs in polynomial time in d over epsilon. Right. So in particular, we showed that even with respect to the Gaussian distribution, there's no algorithm that runs in polynomial in time in d over epsilon. But you would still ask, okay, but what's the best thing you can do in this setting where I don't assume anything on my training distribution? Can you do something? And I conjecture that you can't. That you need, I think you probably need, if I had to guess, you probably need something like 2 to the d. But what about the lower bound of d to the sum? But you cannot do like d to the sum function of epsilon. My guess is that's impossible. So as conclusion, we combine ideas from distribution testing with this other fields in theoretical computer science, where people assume things about distributions, such as uniformity, Gaussianity, and so on. And we show that building on these ideas like k-wise independence, you can develop testers that make sure that you can trust the guarantees of these algorithms on a particular data set. Thank you very much.
Questions?
For your conjecture in the last slide. Can we go back? So is this conjectural exponential or conjecture maybe super polynomial or bound? Is it an artifact of this being distribution free, you think, or of the specific model for Testable?
What would be an alternative model?
I don't know. Just wondering whether.
I can't. The model is kind of really bare bones. Like you would probably want more things from it. I think, for example, like PQ learning, it looks at the samples. It decides like sample on sample basis. It's like I abstain on this sample. I don't abstain on that sample. So you can argue they will want that. But if you have that, you have our model too. So so I think our model is pretty bare bones.
Any other questions? All right, so let's thank Arsen again.